The Micromeritics 3-Flex Surface Characterization Analyzer is a fully automated physisorption and chemisorption analyzer designed to provide a superior understanding of the world's most complex materials. The 3-Flex has the flexibility to perform a variety of analyses, including surface area for mesoporous and microporous materials, static and dynamic chemisorption, temperature-programmed experiments, pulse chemisorption, and vapor isotherms. The 3-Flex's versatility allows an easy and quick switch between physisorption and chemisorption, allowing the user to sequence experiments. It is ideal for characterization of metal organic framework synthesis, zeolites, activated carbons, and more. It is the only instrument in the market capable of running up to 3 samples simultaneously, each one with a designated gas. The 3-Flex is engineered for high performance. The manifold features metal seals and hard seal valves, providing superior evacuation, cleanliness, and chemical resistance. Proprietary isothermal jackets provide unmatched passive temperature control. A dedicated vapor pressure thermometer ensures the most precise analysis temperature and saturation pressure measurements. The high-performance engineered into the 3-Flex provides precise isotherm measurements and characterization of materials with pores as small as 0.35 nanometers to pores larger than 50 nanometers. The comprehensive and user-friendly microactive software allows users to quickly report surface area, porosity, and pore size using the most advanced analysis models. The advanced report system allows users to create Python scripts for custom analyses. Is your laboratory ready for the most advanced, versatile, and precise instrument for measuring surface area, porosity, and pore size? Visit micromeritics.com to learn more about the world's most trusted supplier of particle characterization systems.
Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin and I am the Technical Director at Micromeritics Instrument Corporation. Before we begin, we want to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during this session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Professor Christopher Jones. Professor Jones is currently the John F. Brock School Chair and Professor of Chemical and Biomolecular Engineering at Georgia Tech. In 2010, Chris was selected as the founding editor-in-chief of the highly regarded journal ACS Catalysis, and in 2020 was named the founding editor-in-chief of the new open access ACS journal, JAX AU. Chris has received numerous prestigious awards, including the ACS Ipatieff Prize, the North American Catalysis Society Paul E. Emmett Award in Fundamental Catalysis, the American Society of Engineering Education Curtis W. McGraw Research Award, and the AICHE Andreas Akrivos Award for Professional Progress in Chemical Engineering. His group's current research focuses on materials for energy, including CO2 capture and lignocellulose conversion, heterogeneous and homogeneous catalysis, including the interface of homogeneous and heterogeneous catalysts, adsorptive and membrane separations. Chris, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on direct air capture of CO2 and the important role of porous materials in direct air capture technology.
Hello everyone, my name is Chris Jones. I'm going to talk to you today about direct air capture of CO2 and the important role of porous materials in direct air capture or DAC technology. I'm a professor in the School of Chemical and Biomolecular Engineering at Georgia Tech, and I'm happy to take part in this micromeritics webinar program. So I'll begin my talk with some key messages that I'll then emphasize throughout the talk as I go through my material. The first message is that scientists and engineers, sometimes while we're solving our problems, we also create new ones. And one example I'd like to give you is our solution to famine problems in 1900 that's led to our current population and energy boom, which of course has fueled climate change. So if we look back to about 1900 and we consider what scientists and engineers like us, as well as policymakers, would be most worried about as a global challenge, that global challenge was famine. With seemingly every year significant famines going on around the world leading to many, many deaths. And the public was clamoring for a food solution. And in the early 1900s, Haber and Bosch came along and developed their catalytic process that was able to fix nitrogen from the air. Until the early 1900s, fixed nitrogen for fertilizer was primarily obtained from minerals, in particular nitrate minerals mined from Chile. However, after Haber and Bosch were able to catalytically fix nitrogen from air, we saw that the cost of those nitrate minerals or fertilizer precursors dropped from above $40 per ton to below $20 per ton. And so this solution of science and technology then fueled a very significant population boom. And of course, we know today we've surpassed 7 billion people on Earth. But if we look in the historical record, it took about 250 years before Haber and Bosch for the population to triple, whereas after Haber and Bosch developed their process, we had a fourfold growth in population in less than 100 years. And so our current climate and energy challenge has really been fueled by this prior scientific advance, inadvertently leading to our current climate change problem associated with all of the CO2 we've produced, providing energy for this growing population. So the good news, though, is that history shows that when we're given a big challenge, like Haber and Bosch faced, that science can respond in a rapid and focused way when we're well-resourced. And examples include the Manhattan Project in the 40s, the Moonshot in the 60s, or the Human Genome Initiative in the 90s. I believe that climate change is going to be the defining challenge of our current era, and history will look back and see how we help contribute to solutions to this problem. Among the climate change solutions, one important solution are negative emissions technologies, which take CO2 out of the air. Along with renewable energy, these two items together, I think, are going to provide a significant component of the solution that we need for climate change. And then finally, direct air capture, the subject of my talk today, is a key scalable net, and it's one where expertise in porous materials, adsorption, and their intersection with chemical processes can bring a lasting impact. And I like to think of DAC as today's Manhattan Project or Moonshot. So if we consider the ways we're going to tackle this challenge, there's two approaches that need to be coupled together. The first is emissions mitigation, where we reduce carbon sources, and the second is CO2 removal, where we enhance carbon sinks. So when we're reducing sources, we're taking improvements in energy efficiency as well as low or zero carbon fuel sources such as nuclear, wind, and solar. And then we can couple that with approaches that take CO2 out of the atmosphere in a permanent way. And there's a wide variety of such approaches that have been studied and that have been outlined in the National Academy study that I was a part of on negative emissions technologies and reliable sequestration. So these two approaches, which go hand in hand, offer different products. Emissions mitigation gives you a product called avoided emissions, whereas the development of carbon sinks gives you negative emissions. So in the context of an environmental spill, on the left, we're stopping the spill, and on the right, we're cleaning up all the material that has been spilled before we were able to stop it. So if we consider the development of negative emissions technologies, or NETs, we can ask the question, how large is the potential market for this type of new technology likely to be? And to consider that, we can look at scenarios for CO2 emissions and greenhouse gas emissions in terms of gigatons per year or billion tons per year as a function of time. And we're right about at the apex of this red curve today, around 2020. And if we continue to operate in a business as usual mode, it's predicted that the maximum set of emissions will occur sometime mid-century, at which point we'll start to reduce emissions. However, if we follow this pathway, we're very likely to exceed 2 degrees C warming, which could have catastrophic consequences on global climate. There's a variety of alternate scenarios where one can stay below 2 degrees C, and one of those scenarios is shown here in red. And to make this scenario a reality, we would have to mitigate all the emissions shown in green using conventional abatement technologies, while bringing on a new set of technologies shown in blue, initially being launched at a considerable level in 2030, reaching 10 gigatons per year around 2060, and then 20 gigatons per year around 2100. And this blue swath represents these carbon removal technologies or negative emissions technologies. And if you consider the scale of these requirements, 10 gigatons per year by about 2060, 20 gigatons per year by century's end, we're talking about recreating a new industry from scratch that is going to be roughly 25 to 50% of the size of the fossil fuel industry at various points in the next decades. So this is clearly a huge challenge, and we need to develop these negative emissions approaches. These are several of the approaches that have been outlined in that National Academy's report, and there's some that are natural approaches, such as managing forest land and farmland and coastal ecosystems differently. But these, while being low cost, generally will contribute to only a fraction of the needed negative emissions technologies outlined in the previous slide. And it's relatively certain that we're also going to need contributions from non-natural approaches, such as chemical technologies that focus on the accelerated chemical weathering of rocks, or the removal of CO2 from the air via chemical processes, whereby that CO2 would then be stored underground permanently in geologic formations. So I'm going to focus on DAC, capture of CO2 from air via chemical processes. So if we look at the history of direct air capture of CO2, we note that we've actually been doing this on a smaller scale for quite a long time. And since the early 1900s, we had CO2 removal technologies in place, for example, in submarines, or later in the century for spacecraft. But it wasn't until 1999 when Klaus Lackner, a physicist then working at Los Alamos National Lab, proposed large-scale direct air capture as a climate change mitigation methodology. About 10 years later, the first adsorption-based and absorption-based, so both solid and liquid sorbents, were developed, including Carbon Engineering, Global Thermostat, and Climeworks, which are the big three companies that started around that time. And in that time period, my group at Georgia Tech started working with Global Thermostat to marry our adsorbent technology with their process technology. In 2011, we published our first brief review on DAC separation technologies, and then a much more detailed review shown on the right in 2016. So if we think about this specific separation challenge, it's a challenge where adsorbents can play a huge role in technology development. And the key challenge is that we have an adsorption separation we're trying to achieve using an ultra-dilute mixture. We have 400 parts per million CO2 roughly, with a significant excess of water present in the feed stream because there's significant humidity in the air that varies by location and by temperature. But it can be multiple orders of magnitude more water than CO2. Of course, we have the other components of air as well, and we want to have selectivity specifically to CO2 over all of these other components. We also need a sorbent that's readily scalable and can be made on a very large scale in order to supply the scale of separations that are needed for this application. So in 2009, while we were still primarily focused on separations of CO2 from flue gas, we published a review describing the various sorbents that have been used for CO2 separations up to that time. Shown here is a plot of capacity in moles per kilogram as a function of operating temperature in Kelvin. And you see that much of the high capacity sorbents operate at very high temperatures, far away from ambient conditions, making them perhaps difficult to imagine incorporating into a direct air capture process where you're going to be operating outdoors under ambient conditions. However, when we go to the low temperature regime that might be more amenable to direct air capture processes, we see that the majority of these materials are physisorbents, where selectivity to CO2 over water can be quite challenging, for example, with zeolites, carbons, or moths. However, there's one family of materials that we thought were quite promising for this application, organic-inorganic hybrid materials, broadly speaking, whereby you can begin to take advantage of amine chemistry to have low-temperature chemisorbents. And these chemisorbents, with their significant heats of adsorption, lend themselves towards steep isotherms that give you high sorption capacities even at low partial pressures as needed for direct air capture. So if I outline the 5 needs for a practical direct air capture process, I note them here. And I'll talk about each of these step by step, but given that we're in an audience here where we're all interested in adsorption, I'm going to focus mostly on adsorbent thermodynamics, number 2. Of course, adsorbent kinetics are also important. Developing low pressure drop gas-solid contactors is critically important. And while adsorption is exothermic and happens spontaneously, adsorbent regeneration requires energy input, and so this will be our endothermic step, which will require energy, and we want to minimize that energy that's required. And then finally, we need to have a process and a material that is low cost and long in life, such that we can have overall good process technoeconomics. So we'll begin with the low pressure drop high surface area contactor. So because of the level of dilution of the target gas molecule, in this case CO2, we need to process very large volumes of gas compared to a typical flue gas separation process. And what that means is that pressure drop is going to be a critical factor. A paper written by collaborators studying a hypothetical DAC process a number of years ago estimated that because of the level of dilution, that the overall cost associated with the energy to drive gas flow through the separation system could range from roughly 15 to 35%, showing that you really do need to try to focus on minimizing pressure drop. Fortunately, as a researcher coming out of a catalysis background as I do, one can easily imagine contactors that could work quite well. These ceramic monoliths are contactors that we all own if we own a gas or diesel-powered car, because this is what our catalytic converter has in it, on which we've mounted, in that case, precious metal catalysts in order to clean up the exhaust gas. But we could also just as easily mount sorbent materials on these surfaces, and then achieve very, very low pressure drops on the order of a few hundred pascals at high gas velocities on the order of 5 meters per second. So I feel like this is a component of a good design, and there are other low pressure drop designs as well that we could potentially have readily in hand today. So if we think about what kind of adsorbent we would put on these contactors, I outline for you here 2 types of CO2 sorbents we might consider. A classic CO2 sorbent is zeolite 13X. It's a physisorbent with a low heat of adsorption on the order of 35 kilojoules per mole. And that physisorbent energy leads to a relatively shallow adsorption isotherm at low partial pressures, such that the CO2 uptake is relatively modest. But if we were to go out to higher pressures, of course, zeolite 13X absorbs a very large amount of CO2. For silica APS, that's a classical example of a chemisorbent. So this would be a porous, mesoporous silica functionalized with this aminopropyl silane species. This is a chemisorbent with a high heat of adsorption, maybe near 85 kilojoules per mole. And you can see that this lends itself to a much steeper adsorption isotherm that, while having maybe a lower capacity at higher pressures than zeolite 13X, is advantaged at the low partial pressures that are important to direct air capture. Furthermore, if you remember your organic chemistry, amine CO2 chemistry is operable in all ranges of humidity, and water doesn't compete with CO2 in most cases for adsorption on these types of sites. In contrast, we know that 13X will swamp out the CO2 with water when water is present in large amounts. So when we consider the array of well-known, well-characterized physisorbents like zeolite 5A or zeolite 13X that are quite effective at capturing CO2 under a range of temperatures as well as a range of pressures, we remember that because of the selectivity of CO2 versus water being so important, that these types of sorbents are generally not your first choice sorbents for direct air capture. Of course, you could do a two-bed separation where you first remove the water and then remove the CO2 using these types of sorbents. But if you do the back of the envelope calculations, you recognize that that roughly doubles your regeneration energy compared to a sorbent that can tolerate water and minimize its absorption. So if we think about now a separations process in the chemical engineering context, there are two classic adsorption-based separation processes that are used. One is pressure swing adsorption, and the other is temperature swing adsorption. And perhaps pressure swing adsorption is more well known. However, it's not very efficient when you have an ultra-dilute feed. And in fact, if you were to calculate the separation efficiency, as my colleagues Lively and Ralph did in 2016, as a function of feed mole fraction, one sees that the overall separation efficiency significantly increases for more concentrated feeds. And this makes sense because you're taking the feed and you're putting a lot of energy into that feed by pressurizing the feed. And so you don't want to pressurize diluents, you want to pressurize your main molecule. So it's much more efficient when you go to higher concentrations. In contrast, for TSA, TSA is the optimal approach to use for dilute and ultra-dilute separations. We can see that by these separation efficiencies here, where maximum efficiencies are aligned with different heats of sorption at different feed mole fractions. And if we go here and we drop back to 400 parts per million, we see that the ideal heat absorption for 400 parts per million is somewhere on the order of minus 55 to minus 65 kilojoules per mole, so very close to the heat of adsorption that we might imagine for a good chemisorbent. So I'd like to do a deep dive now on two different types of separation materials that I've used for this application. The first example that we'll talk about will be amine grafted mesoporous silica like SBA15. Here we have well-defined binding sites that are all identical, and that allows us to do fundamental characterization of the nature of the adsorbed species on the surface. However, because silanes are relatively expensive compared to, say, pre-synthesized aminopolymers, when we're trying to deploy these types of materials at scale, it's typically going to be a porous support material. In this case, SBA15 silica is what we use for our scientific studies, that has the pores impregnated in a non-covalent way with a low molecular weight, highly branched polyethylene amine as an example of an amine polymer. So we began to first work on the question, what type of amine would we want to design for this type of separation? So we measured adsorption isotherms, moles per kilogram as a function of pressure for primary, secondary, and tertiary functionalized SBA15, where the surface area, pore volume, and average amine surface coverage are the same for all of these materials. And we see, measuring isotherms at 3 different temperatures, that primary amines and secondary amines both work pretty well, even at the low partial pressures needed for direct air capture. If we take the classical approach to calculating the heat's absorption from these isotherms at different temperatures, we could conclude by application of the Clausius-Clapeyron equation that the primary amines are more effective than the secondary amines because they offer a higher heat of adsorption. They're more exothermic. And so our take-home message from this first work that was done back in 2012, almost 10 years ago, is that primary amines are targeted with secondary amines being okay. And that's worthwhile because we've also found that primary amines are among the amines most robust to degradation by oxidation and other modes. You see, tertiary amines are not here. And that's because these amines require water to be present in order to absorb CO2 via chemical adsorption or via chemical reaction. And these isotherms were measured as a dry gas. So we decided we wanted to test that hypothesis regarding the improvements based on the heat of adsorption between primary and secondary amine functionalized materials. And for this, we used a Ceterom Calvé calorimeter, whereby we could dose in small amounts of CO2 while simultaneously measuring an adsorption isotherm and capturing the adsorption heats. And so by using small pulses, even the first molecules of CO2 that adsorb, we can capture as a function of coverage, their heat absorption. So when we do that, we measure the isotherms and the heat simultaneously. And now I'm going to talk about only a single type of material. So this is SBA15 functionalized with these primary amines that I showed you before were the most effective at adsorbing the CO2. Moles per kilogram is a function of pressure. And what we see is that when we start with bare silica and then begin increasing the density of primary amines, we see relatively no change as we add significant amounts of amines until we get to some threshold value and then a substantial increase in uptake occurs. And this is really interesting because this is a nonlinear response of uptake as a function of amine loading. And while our sorption sites are identical in all cases, being primary propylamine groups, we are changing the site density. And we can rationalize this behavior if we understand the way the CO2 adsorbs on the surface. At low amine loadings, where the amines are relatively isolated, we form carbamic acids, which have a moderate heat absorption and a moderate driving force for adsorption. But then as we increase the amine density, eventually these carbamic acids find another amine present in close proximity, close enough that it can deprotonate that carbamic acid and form an alkylammonium carbamate. And these alkylammonium carbamates are strongly enthalpically favored, and this big jump in uptake is due to cooperative nitrogen-CO2-nitrogen interactions. And so having nitrogens in close proximity is an important design principle for these sorbents that adsorb by this mechanism. We can now follow the heat's absorption as a function of coverage for these same materials. We see that the bare silica is a physisorbent with maybe some weak chemisorption for the first molecules of CO2 that adsorb. And then as we increase the amount of amines, we see this significant jump in the heat absorption, where the material that has the largest surface coverage of amines also has the largest CO2 uptake and the most consistently high heat absorption associated with these alkylammonium carbamates. Okay, so now let's turn our attention to different types of amines, again with the heat absorption on the left now, the isotherms on the right. Moles per kilogram is a function of pressure, and then heat in kilojoules per mole is a function of CO2 adsorbed. And if we focus on the two different regimes, there's a physisorption regime and a chemisorption regime. We'll start by looking at the chemisorbents. And the chemisorbents in this case are a primary amine, the methyl secondary amine that we looked at before, and now an N-butyl secondary amine. We see that they all capture CO2 reasonably well with different shapes to their isotherms. But interestingly, they all have the same heat absorption within error of our measurements. However, previously we had hypothesized that the primary amines were more effective than the secondary amine maps, the red versus blue, because of a higher heat absorption. That's what we had calculated using the Clausius-Clapeyron equation. And of course, our calorimetry tells us that that's wrong. And so if the enthalpy difference is not the driving force for one being better than the other, it implies that entropic contributions are important. And this makes sense if you consider the nature of the adsorbent itself. So by applying the Clausius-Clapeyron equation, we're assuming the entropy of adsorption is the same for all sorbents. But that's not the case when your binding site can move and wiggle and has motion associated with it. So in this case, in order to bind CO2 in this alkyl-ammonium carbamate structure, if this is a secondary amine, this H group becomes an alkyl group. We have to get that alkyl group out of the way in order to form this alkyl-ammonium carbamate. And those steric hindrances can manifest themselves with regard to entropic barriers that must be overcome in order for capture. In fact, if we make that entropic barrier significant, so this is a cyclohexyl group now, which is not that different electronically from the N-butyl group, so similar basicity, similar driving force to bind the CO2. But now the group is so big you can't form these alkyl-ammonium carbamates, and the material just acts like bare silica, like a physisorbent. Same thing happens if you make the basicity much weaker by putting a phenyl group here. So this tells us the ability to form carbamates correlates with our high uptakes that we seek. With this type of knowledge, we've now designed a wide array of different small molecule as well as oligomeric amines for CO2 capture. A swath of these are shown here. These would all be molecules that we would incorporate into the pores of a porous silica or alumina support in order to capture CO2. I'll now turn my attention to characterizing the type of materials that we want to deploy on a large scale, where we physisorb the PEI inside the pores of the support. For these materials, characterizing the hard component, the SBA15, by X-ray diffraction, TEM, or nitrogen physisorption is relatively straightforward, and tools are readily available to do that. However, in this hard-soft composite, the soft component, the polyethylene imine, which in this case has a consistency like honey, is very difficult to characterize. And there aren't very many tools that are available. We chose to exploit the high neutron scattering cross-section of deuterated PEI to try to get an idea of what does the PEI look like when we put it in the pores. And this is going to be very important to the gas adsorption-desorption process and any diffusion limitations that may develop. You can imagine two very different scenarios, one where you perfectly coat the walls and one where there's no coating and you just form plugs. And we can model all different arrangements in between these two end members of a distribution. We're able to do this because we've made synthetic deuterated PEI with properties very similar to the commercially available HPEI. And we can then measure the neutron scattering for the bare silica as well as the PEI-loaded silica for 5 different materials with 10, 20, 30, 40, or 50 weight % PEI. And then go ahead and model what the diffraction pattern should look like as we put PEI into the pores in different structures. Now, if we were smart enough, we would have figured out the answer just by analyzing these data from our nitrogen physisorption instrument. So in this case, we are looking at the disappearance in the porosity of the SBA15 as we load in more PEI. You see, even at 50 weight % loading, we have a little bit of mesoporosity. And if we look at the change in the pore size as we move from low loading to high loading, we see that the pores first narrow and then they stop narrowing and the total area under the curve sinks into the baseline. And this alone should have told us what the PEI looks like as it goes in the pores. But we had to couple this with our neutron data in order for us to click, for it to click in our mind, for us to understand the distribution. And what this tells us is that roughly the first 20 volume % of PEI that goes in coats the walls because there's an enthalpic driving force for that to occur. You've got weak amines in the base, weak base sites associated with amines in the polymer, and you've got silanols and weakly acidic sites on the walls of the silica. So you coat until you've completely coated the silica, at which point the next PEI that comes in only sees other polymer, so it will begin to aggregate with itself. And as this plug grows in size, what we'll see is a reduction in pore volume without any further narrowing of the average pore size, totally consistent with our nitrogen physisorption data. So, I showed you a lot about adsorbent thermodynamics. I'm now going to step through these last three pieces relatively quickly and then end with one more adsorbent material characterization component before I finish my talk. So let's talk now about kinetics. We need to cycle the CO2 on and off these materials as quickly as possible. And we need to process a lot of air in order to make this practical. So at 70% capture, where we're capturing 70% of the CO2 that passes through our process, in order to get 1 ton of CO2, we need to process 3,500 tons of air. And for that reason, we use these monolith contactors. But in the lab, we use a TGA typically. And if we look at a normalized TGA equilibrium capacity as a function of time for 400 ppm and 10%, you see it takes many, many hours to get to a pseudo-equilibrium. But for our kinetic separation, we want to stop the process at about 80% total capacity to 80% equilibrium capacity, and then desorb and cycle the material between low loading and about 80% loading after we're starting to exit this linear regime of uptake. So that will take more than 100 minutes in a TGA, but if instead of operating in a TGA, we're operating at 5 meters per second in a monolith, we can get that capacity down to 15 minutes. And so the combination of a monolith coated with effective adsorbents based on amines means we can have a cycle time on the order of 20 minutes or 3 cycles per hour. So to regenerate, we need to put energy into the system. Adsorption being exothermic is spontaneous. The good thing about regenerating these amine materials is we only have to heat to, say, 70, 80, 90 degrees C. So that means we can use low-grade heat that is readily available from a wide variety of processes. We'll use that low-grade heat, which we can get from processes as shown on the bottom, to make saturated steam. That steam will be passed through the monolith, where it will condense on the monolith surface, conduct heat into the structure, thereby liberating the CO2 and desorbing the CO2, giving us a steam CO2 mixture, which we can then condense and compress to give us our purified CO2 stream for sequestration. And then finally, we have to do this all on a scale that is practical. And so Global Thermostat has developed 2 different units shown here, their first generation and their second generation units. This actually is a 3rd generation on the right. One in Menlo Park, California in 2011-2012, one in Huntsville, Alabama in 2018-2019. Global Thermostat, this technology startup, uses our sorbents under license in their commercial scale air capture process. They used to have their R&D labs in Atlanta in my building, and they've recently moved to Brighton, Colorado. And the Georgia Tech requires that I point out my conflict of interest in that I receive research funding for Global Thermostat, and I have a financial interest in Global Thermostat as well. So if we think about that process, we need to have a process that can produce CO2 at a relatively low cost. We've modeled such a process with my colleagues in a series of papers here using Mil 101 chromium polyethylene amine, so a MOF loaded with polyethylene amine, in a 5-step process by experimentally fitting adsorption isotherms, modeling ambient air at 400 parts per million at 25% relative humidity. We had a 40-minute cycle time, and we found an energy of separation of about 0.15 megajoules per mole CO2. These processes for direct air capture are relatively simpler than processes for conventional CCS because of the fact that we don't have to do as much heat integration. We can make them in a mass manufacturing type of paradigm rather than making large units. We can mass manufacture smaller units. And what's promising is even though we're about 400 times more dilute in CO2, we're not 400 times more energy, because if we design the process for a dilute feed on purpose, we can make the energy required actually quite low, only 1.5 to 2.5 times more than the post-combustion solvent-based process, as an example. So if we break down these costs into components, one of the biggest unknowns is the cost of the sorbent, because the exact sorbent that would be used on a large scale is still being determined. and the lifetime of that sorbent is still unknown. And so it could be quite low in cost or quite significant in cost, and this is something that our R&D is currently trying to suss out. Nonetheless, we calculate that an nth plant, so this is a mature technology 20 plus years from now, could have a cost on the order of about $100 per ton. Others are seeing the same thing. This is a recent paper by Ghazani published in Joule, where they projected both solid and liquid sorbent DAC processes can achieve costs under $200 a ton. Most costs quoted today publicly for the first of their kind plants are typically between $500 and $1,000 per ton. So these were the 5 things I said we needed. We've demonstrated them all in the laboratory or in the pilot scale, but there's a few of them that have room for significant improvement. For example, minimizing the energy of regeneration, reducing costs associated with the process and the sorbents. But of course, there can also be incremental advances made in other areas with low pressure drop contactors, good adsorbent thermodynamics, as well as good adsorbent kinetics. So one of the big questions that I always get when I talk about this is whether or not this is going to require a lot of land or some other types of constraints. And so if we consider doing some basic calculations, assuming that we're going to do the whole world's negative CO2 emissions with direct air capture. I don't think we'll ever do this. I hope we never need to do this. But let's say none of the other negative emissions technologies seem to scale very well. Well, if we were to try to do all 10 gigatons, which is the 2060 target by DAC, we calculate the land area that would be required for this for, say, typical global thermostat or Climeworks technology, and it's about 150,000 square kilometers, which is roughly the size of Georgia. So I'm not arguing that we should use Georgia for this purpose or the state that you live in, but what I would argue is that this land area required for a technology that is critical to the global health and global climate is reasonable. And in fact, we can probably find that much unused and appropriate land around the world without having to displace many current activities that are currently going on. And so while I don't want to have DAC do the full 10 gigatons per year, I think it would be possible from a land area perspective. The second question I commonly get is, why don't we use natural systems like trees? We should use as many natural systems as we can. Unfortunately, as a species, we are very good at destroying forests, not very good about replanting forests, so we have some work to do there. But we should try to do as much of the natural solutions as we possibly can as a starting point. However, the DAC process is actually quite efficient compared to a tree at the equator. So if you go to the literature and calculate what the CO2 removal flux of a tree at the equator is, it's about 20 micromoles per second per meter squared ground area, whereas the DAC process generates about 500 micromoles per second per meter squared ground area. So it's actually, from a land area-based footprint perspective, significantly more efficient than a tree at the equator. Okay, so I'm going to finish with a new direction that we started to work on, and this is the potential for advantages in temperate or cold climates. And if we look at the literature of where everybody has studied direct air capture, it's mostly around 20 to 30 degrees C, which represents a very narrow range of climates in the US. And unlike most chemical processes that we're used to thinking about, where there's one set of optimal conditions that are the same everywhere a process is operated in the world, because we say control it to be 200 degrees C and 5 bars of pressure because we can. For direct air capture, we need to deal with the ambient air with as little pretreatment as possible to make the costs reasonable. And ambient air as a feedstock, however, is wholly and widely variable all over the world. So I show you here the temperature variations as a function of time for different regions in the US, ranging from about -20 to about 30 as an average temperature. And then also you have huge variations in humidity, where the absolute humidity varies by a very significant factor from the coldest temperatures to the warmest temperatures. And then, of course, we have arid zones as well as humid zones. So previously, we developed Mil-101 chromium loaded with polyethylene amine as a fairly useful CO2 sorbent, absorbing about 1.3 moles per kilograms of CO2 at 25 degrees C using 400 ppm feeds. We've recently found that there may be ways to reduce the energy of separation by operating under colder climate conditions. So if we were to target cold climates in particular, we have two advantages. One, we can drive more physisorption, and two, we can minimize the amount of water that's present in the air and thereby reduce the amount of water that absorbs on the sorbent. So here we look at Mil 101 chromium with the uptake at 400 ppms in a volumetric system using either polyethylene amine or tetraethylene pentaamine at 25 degrees C and minus 20 degrees C. And when we go from 25 degrees C to minus 20 degrees C at 30 weight percent amine loading, we see a significant uptick of CO2 absorption. And at this low temperature, minus 20 degrees C, we see significant physisorption or weak chemisorption from the CO2 temperature program desorption plot, where we're showing you the CO2 concentration as a function of temperature as we ramp the temperature from minus 20 up to, say, 100 degrees C. So for these sorbents, we see that the CO2 comes off at relatively low temperatures. And so this could allow us to imagine a scenario where we go to a cold region, say Alaska, and can operate with a sorbent that combines physisorption and chemisorption to give good uptakes with relatively small temperature swings for desorption. We can look at these materials in a breakthrough process as well. So here's the CO2 breakthrough curve for 400 ppm CO2 under dry conditions in red, and then at 70% relative humidity at minus 20 degrees C. The black line shows you the breakthrough of just the blank reactor. So you can see there's significant CO2 that's removed under both dry and humid conditions, and that the humid actually allows a faster return to equilibrium conditions, a sharper breakthrough than operating under dry conditions. If we calculate the capacity in moles of CO2 per kilogram of sorbent, we also see a significant increase in the breakthrough capacity as well as the pseudo-equilibrium capacity at minus 20 degrees C when we go from dry conditions to humid conditions. So like other amine-based chemisorbents, moisture has a positive effect on capacity of subambient DAC, even at high relative humidity using these materials. These are conditions where a zeolite would almost certainly fail to capture good large amounts of CO2. And we can look at the desorption of these materials, and what we see is that the enhanced CO2 absorption under humid conditions is mostly attributed to a new peak at that goes from 20 to 35 degrees C. And this new peak starts after significant water desorbs, as shown in this dotted line here. So these data suggest that we are chemisorbing CO2, and that the additional CO2 uptake in the presence of humidity might be associated with bicarbonate formation, and we plan to do in situ IR to probe this hypothesis. So I'll finish here. I'm excited about this topic because direct air capture requires classical chemistry and chemical engineering skills, and it's very relevant to the porous materials community. We need sorbent materials that are CO2 selective, high capacity, offer rapid sorption-desorption with the lowest feasible heat of adsorption, low heat capacity, and high thermal conductivity. And I think that as we think about the different eras of technology in the past, carbon management and energy will be the defining problem of this current generation. I'll end by inviting you to please consider attending the Fundamentals of Adsorption Conference next May in Broomfield, Colorado. There will be significant applied and fundamental research presented on adsorption, as well as a large section focusing on CO2 capture, in particular CO2 capture from air. I'll thank my senior collaborators on the left, as well as my former students and postdocs who have worked on CO2 capture from various sources. I published a few reviews on the right-hand side that might be of interest to people. And finally, I'll thank those who funded my work, shown on the right, as well as my last group picture before the pandemic, which was one of the last times we were able to get together for a picture without masks. So with that, I'm happy to take any questions, and I really appreciate the opportunity to present my work to you, and hope you found it interesting. Thank you.
Thank you, Chris. I'm opening the chat for everyone's questions now, and we already have a few. Chris, what do you think is the biggest roadblock currently limiting the pace for direct air capture development?
Yeah, thanks for the question, and I appreciate the opportunity to present. I think that there's great room for improvement in incremental ways on all of the topics that I discussed today. But if we want to imagine deploying this as a technology quickly, I think the most important thing we need to do is to build and test pilot scale equipment, learn what works well from it and what doesn't work well, go back to the lab and redesign our process and our material, and basically cycle through technology generations as quickly as possible. So up until this point, a typical DAC technology generation is on the order of 3 to 5 years. For us to meet the 2060 target that I talked about in the presentation, we probably need to drop that to a year or less. So hopefully we can do that by combining work on materials, processes, and pilot scale testing.
Thank you. You showed different support materials, zeolites versus potential zeolites versus silicas versus moss. What are the prospects for practical deployment of these materials for direct air capture?
Sure. Thanks for the question. So if we actually imagine developing this technology at the scales I described, any such material that's made today is going to have to be massively scaled up. So as a starting point in the near term, materials that are already made at scale and or can be made at scale quickly will be quite important. Also, this is the ultimate of commodity processes, such that we're really trying to minimize the amount of money we're going to lose in the form of a carbon tax or in the form of CO2 cost. So probably it's not a lot of room for very, very exotic chemistry. So I think any porous silica, alumina, other metal oxide material that can be made at scale is promising. I think that you can imagine scenarios where moss could work if you're dealing with earth-abundant metals and low-cost ligands. And then, of course, zeolites have been made at scale for a very long period of time, as well as carbons that also could be potentially useful. So I think there's a broad swath of materials that can be deployed, but we will need to make them, any material we choose, probably at scales that are orders of magnitude higher than we make today.
So the next question is really sort of how does this affect everybody currently? You showed this really nice number of potentially getting to $75 to maybe $140 per ton of CO2. If we had to think about that in terms of what's that kind of additional to if you pay for a gallon of gas? What would that tax look like per gallon of fuel? Has anyone done that calculation?
Yeah, those calculations have definitely been done, and I don't have that immediately in front of me, but trying to think back, because I have that in slides that are buried on my computer. And the example was done in the context of jet fuel. And if I remember correctly, it was on the order of a dollar per gallon of jet fuel. So you can imagine translating that to motor fuels, personal motor fuels as well. It's probably on that order of magnitude if the cost were on the order of $50 to $100 per ton. Another way to think about it is if you think about it in the context of global GDP, the carbon capture challenge is on the order of 1% or 2% of global GDP. So it's not an insignificant cost, and this is one of the reasons why, as a global society, we have delayed, and as a consequence, that's why we have all this built-up CO2 in the atmosphere.
So next question gets back to production of these materials. What does the carbon footprint look like for the production of some of these sorbents?
Yeah, that's a great question, and I think this is a really fertile ground for research. We are doing our first comprehensive LCAs now in the context of a DOE project that we have, whereby we're taking CO2 out of the air via direct air capture to feed to algae bioreactors in order to make algal-based crops for bioenergy. And as a component of that, we're doing a comprehensive LCA. So we have not yet published that. It's not entirely finished. And as you can imagine, there's a lot of factors that go into it. And certainly one factor for the types of materials that I use is the lifetime of the sorbents, because we know that amines are not thermodynamically stable under ambient conditions. And whether they last 6 months, 12 months, 36 months will have a big impact. But actually the most important thing really is the carbon footprint of the energy sources you use for the actual operation of the process. And so whether you use renewable electricity and renewable heat or fossil-oriented electricity and fossil-oriented heat, that has the biggest impact on the LCA. And in general, the other factors, such as the sorbent materials, are much smaller components of the total carbon footprint.
Okay. The next question really to some of the species that are formed. How did you confirm the formation of the carbamic acid versus the carbamate? And was this done experimentally, and did anyone do any modeling to confirm it?
Yeah, so there's definitely DFT studies that are in the literature. We have not done those DFT studies in the context of our work. We have done a tremendous amount of both in situ NMR and in situ IR. And IR data in the literature is the most prevalent. There's probably work from a half dozen to a dozen different authors who've looked at these types of amine materials via in situ IR under both humid and dry conditions. And the carbamic acids are mostly occurring under dry conditions, and they're much less prevalent in the presence of humidity. And if you follow the chemistry from solution literature and try to extrapolate that onto surfaces, you would imagine that in the presence of humidity, you would see a lot of bicarbonate that forms as an additional form of adsorbed CO2. And we have identified that bicarbonate both via NMR and IR, but we've also been surprised that even under conditions where there's a lot of humidity and there's a lot of sorbed water, that you still do form a significant amount of carbamate, and that it appears that carbamate still is the dominant form of CO2 adsorbed at short cycle times. So yeah, the best way to look at the structures of those materials is via those in situ spectroscopic approaches.
Okay. So I think in one of your latter slides, you showed some TPD and you had some water desorption as well as CO2 desorption during on some of these materials. Do we have an opportunity to effectively capture water as well as CO2 with some of these processes?
Yeah, you definitely do, depending on the climate and depending on the type of sorbent material you use. If you look at the range of technology startups in the adsorption space today, there's a very large number of startups that are focusing on the, quote, water from air concept, whereby materials in very arid regions even can extract significant amounts of water from the air. Well, the DAC sorbents can also do the same thing, either by design or by accident. And some processes do produce water as a co-product. Others don't, due to the nature of the process itself. And so that's an additional factor that one can put into their technoeconomics, is the demand for water in the particular region of operations and possible production of water as a co-product. The nice thing about this process from a chemical engineering perspective is there's so many variables around which one can optimize that you can imagine 5, 10, 15, 20 different solutions that could work in different climates under different conditions. And so I think there's really a lot of opportunity.
Can you share a little bit, if you've got any information on life cycle of some of these sorbent materials? We've got a number of questions where people are asking typical life cycles or expected life cycles.
Yep, so I can surely comment on that. And this is one of the trade-offs that one has to imagine when designing a particular process. So for example, if one uses wholly inorganic materials, like a zeolite or a carbon, one can imagine extended life cycles, and you might choose that as a positive, even if the overall per cycle operation is maybe not as high as a more organic material like a supported amine. And so we and others that I'm aware of have run supported amine materials under real conditions for extended periods of time, months into years. But there are also examples where working with materials like amine materials where due to a process upset or some unfavorable environmental factor where things degrade more quickly. And really for amine materials, you're looking at traces of stronger acids like SOx and NOx. Generally, those are very low in ambient air, so as long as you're not next to a highway or something like that, it's not really a huge problem. But you also have that readily available oxygen. And so actually process control in an amine-based process is quite important because you want to eliminate cases where you have combinations of high temperatures and high oxygen partial pressures, which will ultimately lead to oxidation of the amine polymers and reduction of basicity and therefore reduction of uptake. So yeah, there is, you can operate these amine materials for long extended periods of time, but you also have to be cognizant that they in some ways are more fragile than if you just use something like activated carbon.
Okay. One of the attendees asked, have you considered using two different amines, so using perhaps some PEI and some TEPA with MIL 101?
Yes. Studies are ongoing.
Okay. Is there anything in our air that basically can decrease the life of some of these adsorbents? Do you have any concerns about the trace components there that could damage the adsorbents?
Sure, good question. And this is exactly why more and more pilot scale operations under real ambient conditions is important. Is of course the air contains all kinds of wind-blown materials that one could consider to be a potential challenge, and it's highly location dependent. So whether you are in a dusty, more arid region where you have to worry about particulates, dust, dirt, and grime, whether you are in a more green and humid and lush condition where you might worry about leaves, insects, pollen, all of these are things that are hard to study in an indoor environment, a typical university or national laboratory setting, but that are critically important to the long-term operation of these types of processes. And so, yes, these are definitely something that needs to be taken into consideration, and it's one of the reasons why piloting units in different climates around the world is so important.
We've got a question that goes back to the support material. What's the minimum surface area you need for some of these supported amines to make a good performing adsorbent?
Right. So if you're talking about a carbon or a zeolite, you're really combining pore size engineering along with active site engineering in order to create the right binding site that's going to be selective for CO2. In the context of these amine-based materials, I think more commonly about average pore size and pore volume as being more important than surface area. And the reason is that I'm trying to incorporate small oligomeric amines into the pore space and disperse it in an appropriate way such that it can have good gas-solid contacting. And the amines that are the most productive are the amines that are in the pore space but not in strong contact with the pore walls. And so in that context, engineering the right average pore size and the right pore volume is important. And that's an area where some of the startup companies have a lot of expertise in intellectual property. So it's not something we generally talk about publicly, other than to say that those factors are important.
So we're almost out of time. We actually ran over a little bit. So one final question for this morning. Someone asked, why does capacity decrease after subsequent regeneration on some of these processes?
Yeah. So it depends on the particular case that you're thinking of or the data set that you saw that you're referring to. But in general, for all of these processes, you get to a sort of pseudo-steady state cyclic adsorption-desorption capacity. And that's when the sorbent, after going through many cycles, is easily able to reach its typical cyclic steady state surface loading of CO2, water, oxygen, anything else that's going to adsorb. And so when you start with a pristine material that's clean, you typically see some uptake that's higher in the beginning. And then when you go through the multiple cycles, you may not be desorbing all the CO2 in every cycle, and eventually you approach a cyclic steady state as you do adsorption, desorption. So that's one reason. Another reason could be, for example, if you imagine that there's a trace amount of contaminant that's in the gas that you're working with, if that contaminant is, say, an acid, it's going to stick to the most strongly basic sites and maybe poison those. Maybe once those are poisoned, then the next set of basic sites are left to continue operating, and maybe those are not going to be as easily poisoned. You also can have some cases where you have traces of contaminants that poison the materials as well. So there's lots of reasons for that. At the end of the day, what you want to have is a cyclic steady state that you can achieve after n cycles that hopefully will last for 10 to the 4th, 10 to the 5th, 10 to the 6th n cycles.
Okay, that's all of the time we have for questions today. If we haven't been able to get to your questions, one of our application team will be in touch with you shortly. Chris, is there anything else you'd like to mention this morning?
Just to remind everybody that I think there's a great opportunity to learn more about this field at the Fundamentals of Adsorption Conference that will occur in May. There is going to be a very significant session on CO2 capture in general, as well as CO2 capture from air. And I expect most of the major DAC companies will be present at that meeting. And there may be opportunities also to visit some of the DAC sites that are in the vicinity of the meeting location. So I hope to see many of you at that conference, and I hope you all have a great year.
Great. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we'd be grateful if you could complete the survey, which we will distribute in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again very soon. Thank you all and have a great day.
Thank you, Jeff.